Okay, so welcome back everyone to the Colloquium, and welcome Sara Maloni from who will have the pleasure of hearing talking about Polyhedra, inscribed quadrics and their geometry.
Thank you very much. Thanks for the invitation and for coming here, the first day of the semester. So, okay, so the things I'm going to tell you today is a joint project with Jeff Danciger and Jean-Marc Schlenker. Jeff is in Austin and Jean-Marc is in Luxembourg. And somehow I will tell you a bit of the history behind the problem. And you will see that the question we studied is a very simple question to state. And I will try to tell you a bit of the tools we use to answer the question. And yeah, okay, so let's say going back to Steiner in 1832, somehow he was asking, given a graph, how do we know if this graph can be obtained as one skeleton of a polyhedron inscribed in the Euclidean space? And already this question, the full answer arrived almost 100 years later by Steiner, that proved that gamma is a graph, is a one skeleton of a polyhedron, if and only if it's tree-connected and planar. Okay, so planar is that you can embed in the sphere, and tree-connected is that if you remove two vertices, then it stays connected. And this is a known example. So this graph is clearly not even planar, but also not tree-connected. Okay?
So the parentheses or the convex corresponds to this.
Yeah, so somehow here is not. You can't see a polyhedron because it doesn't satisfy this condition. But yeah, so the vertices are the dots and the edges are the, yeah, we will see how the other. But so, okay, so now we can go farther because somehow when you have a polyhedron in R3, then you can ask, okay, so which one of these graph comes from polyhedra inscribed in the sphere? Okay? So this is what I mean when I say inscribable in the sphere. So which graphs are the one skeleton of polyhedra inscribed in the sphere? And again, Steiner, he showed that not all tree-connected and planar graph are, okay? I need to be, yeah, I tell you some assumption I will have. So when I will say polyhedra, I will always assume my polyhedra to be convex. So I will not stay convex anymore, and that's a big difference. In particular, convex polyhedra are rigid. And the other assumption is that I will, from now on, all my graph will be planar graph, okay? So I will not state it again, okay? So then this is an example of a graph that you cannot embed in this. You cannot realize as one skeleton of a polyhedra inscribed in the sphere, okay? Actually, you can just take a cube and cut one edge, one vertex. And okay, so, but then we still have to answer properly, so that was a partial answer. And actually the full answer arrived much later. It arrived in 1992, and it was answered by Rivin. And the idea is that whenever you have a polyhedron inscribed in the sphere, you can think the sphere or the ball as the projective model of hyperbolic geometry. And then projective model, then lines are small geodesic are straight lines. And so an ideal hyperbolic polyhedron corresponds to a polyhedron inscribed in the sphere. And so what Igor did, he classified those polyhedra. Okay? He classified in terms of dihedral angles and in terms of the metric induced on the boundary. And on the other end, we are speaking about projective geometry. So the sphere is an example of a quadric, but there are two more. Okay, so what about other quadrics? Okay, up to projective transformation, we have two more quadrics to understand, which are the cylinder and the hyperboloid. okay? And what we did with Jeff and Jean-Marc, we answered this question using two new geometry, which are anti-de Sitter geometry and half-pipe geometry, okay? I will introduce everything, but you should think anti-de Sitter geometry as a Lorentzian analog of hyperbolic geometry. And I will speak how you can translate from one geometry to the other. And in fact, this half-pipe geometry, you will see it as a limit of anti-de Sitter or hyperbolic geometry, okay? And I will tell you actually another problem that we were looking at and why we ended up answering this question instead. And these are just some example of polyhedra inscribed in those quadrics, okay? They look a bit funny because as you see, there are two different colors in the graph, and you will see the different role of the red or the blue edges, okay? And so in particular, let me emphasize one thing. So if you think the cube, so you can put the cube in the sphere, and you can think, yes, and I can also put in the cylinder. But probably the way you want to put it in the cylinder is not what I want you to do, because if you put it as the usual cube, then edges will be put in the boundary, okay? So instead inscribed, you just need to touch the boundary in the vertex, in the vertices, okay? So you will be able to put the cube, but we will see why. Okay, so that's the answer. Okay, so what we find out is that a graph is inscribable in the cylinder if and only if it is inscribable in the hyperboloid, if and only if you can inscribe in the sphere and it has an Hamiltonian cycle. Okay, so an Hamiltonian cycle is a curve that passes through each vertex exactly once. And in fact, these are the role of the red edges. And okay, so you can think, okay, yes, first, so it seems like more or less these three conditions are just similar, right? So we are having the Hamiltonian cycle condition, but we will see that actually this Hamiltonian cycle will play a different role, for example, computationally, so it will be very different. And the other things you can ask is that, okay, Sara, yes, so you are having some conditions, so this existence of the Hamiltonian cycle, but who tell me that maybe it's true that all graph that you can inscribe in the sphere, maybe they all contain an Hamiltonian cycle. And if that is the case, I'm not adding anything here. Okay, and actually is a difficult answer because in fact, if you consider graph of vertex less than 18, I can tell you that all the graph inscribable in the sphere, they all contain an Hamiltonian cycle. And for a long time, people think that that was the case. But that's not, okay? So this is an example of graphs with 19 vertices, which you can inscribe in the sphere, but that they don't contain an Hamiltonian cycle, okay? And that's one of the reasons why I'm doing a slide talk, so I would not draw all of this picture. And here, actually, is a picture if you also want all your faces to be triangles, okay? And in fact, as far as I know, it's still open the question if you ask what's the minimal number of vertices for a polyhedron to be inscribable in the sphere and not contain an Hamiltonian cycle. So here is an example with 20, and the conjecture is that this number is between 18 or 20. But yeah. Okay, please stop me if you have a question or I'm going too fast. Okay, so here what I was telling you before. Okay, so in the case of when Igor proved his theorem in 1992, then in joint work with Hodgson and Smith, he also proved that the question, given a graph, can I inscribe the graph in the sphere? This question you can answer in polynomial time, okay? But Dillencourt, he proved that whenever you have a graph inscribable in the sphere, the question, does it contain or does it not contain an Hamiltonian cycle, this question is NP complete. And this makes our answer, our problem, NP complete. So it's much, much harder. And I understand why we need the Hamiltonian cycle, so I'm going to explain to you that. But if you ask me, what's the deep reason why this problem is much harder? I don't think we really understand that, because in some sense, you think the sphere and probably has something to do, certainly has something to do with the geometry and the non-convexity, okay, so that's just one thing to notice, that the two conditions are makes things different, okay? So what I'm going to do now, I'm going to introduce the geometry that we use. So I will start with the hyperbolic geometry that I'm sure you know, but just I tell you how I think about in this context, so with the projective model. And then I will introduce the two new geometry. And then I will state precisely Igor-Rivin theorem, our theorem, and I will give you an idea of the proofs. Okay, so hyperbolic space. Okay, so we can consider the ball. So we consider R4, and we put the 3-1 inner product. The inner product with signature 3-1, and then we consider negative vectors, and then we divide up to scaling. Okay, so this is what is here the hyperbolic tree space. And then here I'm just putting an example of a distance that is small. The distance that you put that you might recognize as the Hilbert distance, okay? So you have 2 points in hyperbolic space. You consider a line between them, and then you consider A and B, the 2 points where the line touch the boundary, and then you have the distance between the 2 points is 1/2 of the log between A and Q, P and B, divided by the distance between A and P and Q and B, okay? And I'm not going to do a short course on hyperbolic geometry. I just tell you few flavor, but somehow these signature 3-1 give you that the isometry group is the group PO31, okay? And on the right, you can just see a tessellation of the hyperbolic plane with polygons in the projective model, okay? So you will see that what we are going to do is that we are going to do exactly the same things, but we are going to change the signature of your metric, okay? So that's anti-de Sitter space, okay? We take again a point in R4, this time with the 2-2 inner product, up to scaling, negative vector up to scaling. And somehow you can see, for example, that the boundary of this space then is clearly our hyperboloid. So you take the vector where the point, the inner product is, it is 0, okay? And the isometry group is PO22. And one very important point of this is that if you consider, for example, the x1, x2, x4 plane, then you have an embedding of an hyperbolic plane inside your geometry, okay? So if you think the equator in your hyperboloid model, that's an H2, okay? And so this space has a metric that is Lorentzian, so it has signature 2-1. And so a vector can be time-like when their inner product is negative, light-like when the inner product is 0, or space-like, okay? So in particular, the H2 inside the space, somehow it's, you should think as the space-like plane in your geometry, okay? And I just want to emphasize a few differences with the hyperbolic space. So in hyperbolic space, somehow is a ball, so it's convex. So to do a polyhedron, you just choose a finite number of vertices, you take the convex hole, and what you get is a polyhedron. Here is not true anymore, because if you choose your point badly, then you go outside your space, okay? So first things to notice. So in particular, the points, the vertices need to be in space-like position. Second difference is that the angles, so in hyperbolic geometry, if you look at dihedral angle, it will be numbers between 0 and 2 pi, okay? Here, no, here angles are real number. And why, for example, a good reason to see that is that in hyperbolic space, you take a geodesic, you look at the isometry group that fix these geodesics, and this group is an SO2, okay? So it's a compact group. Here, the same question give you an SO11, okay? So a non-compact group, okay? And somehow to understand what is positive and negative is a convention that you have because you have your light, your cone of light or time-like direction, and you see how planes look. But so this is not very important for the talk, okay? And for example, somehow this is a geometry that people that study physics, they like a lot. So is a geometry very important for Witten, for example. And okay, and now this more mysterious geometry, okay? Not many people know anti-de Sitter, but certainly more than the people that they know half-pipe geometry, okay? So, and actually I will tell you probably a bit later, after this, I will tell you also this transition geometry, okay? So the half-pipe geometry is a limit of both anti-de Sitter and hyperbolic geometry, okay? And I will explain like how similarly it will happen between a limit of hyperbolic and spherical, U limit to the Euclidean geometry, okay? I will explain later. But so the point is that here you do exactly the same process as before, but your inner product is degenerate, okay? And so then you have this space that the boundary is a cylinder, and again these x1, x2, x4 plane give you an embedding of H2 inside your space, okay? And again the faces are space-like and the dihedral angle are real number, okay? So in fact we will see that this existence of the Hamiltonian cycle is really due to this time-like direction condition, okay? And on the bottom you can see a deformation of the paraboloid model of the hyperbolic space to what it looked like in half-pipe. Okay, so if you go skiing, that's or doing snowboard stuff. Okay, that's the name why. Okay, so and as I promised, so what is this idea of transitioning from one geometry to the other? Okay, so the idea is that some geometry lies inside some bigger geometry. Okay, so for example, hyperbolic geometry is a special case of projective geometry. Okay. And so let's consider the case of hyperbolic and spherical geometry. And let's consider a very simple case of, let's take an hyperbolic triangle with the 3 equal angles. So you can start with an ideal one, so angle 0, and then you can increase the angle, okay? When you increase the angle, actually the area of your triangle becomes smaller and smaller, okay? And until this triangle collapses, okay? So here in the picture, I double the triangle along the edges to have a sphere with 3 points removed, but that's the same. And so when you increase, then your triangle collapses. So it becomes of area 0, okay? But is area 0 in hyperbolic geometry, but if you look with the glasses of a person studying projective geometry, then you can zoom in at the point. Okay, so what I mean is that you act by projective transformation that in some sense make you see what's really happening at the point. And when you do that, actually what happens is that you see an Euclidean triangle. And then the same is if you start with a spherical triangle and you decrease the angle until it collapses, and And so that's what I mean when I say that Euclidean is a limit of hyperbolic and spherical geometry. So in particular, what I wanted to sell you, and I will try to sell back again later on, but in hyperbolic geometry has been studied a lot, and there are things very interesting. And but then the same question, if you understand how to interpret the right translation, then you can ask the same question in this new geometry, and most likely you can find something very interesting. And so this is the case of dimension 2, so surfaces. And then Jeff Danciger, that is one of my collaborators, in his thesis, he studied the case of dimension 3. So he studied the degeneration from hyperbolic to half pipe, or going into anti-de Sitter. Okay? Okay, so now we are ready to state the theorem. Okay, so stating Igor Rivin characterization, our characterization, and then see the point. Okay, so one tool that we need to use is the notion of a dual graph. Okay, our graphs are planar graphs, so we embed them in the sphere. And then what you can do is that you can associate it another graph. You can put one vertex for each face, and then you put an edge between two faces if they are adjacent. Okay. Here are two examples of that. And just one thing that it will be important later. So if you can see a vertex in your original polyhedron that corresponds to a face in the dual graph. Okay, so we will use that in fact. And we will also use that the set of edges of the graph, it coincides with the set of edges of the dual graph. Okay, so this is the characterization of ideal hyperbolic polyhedra in terms of dihedral angles. Okay, so we have a graph gamma, and E of gamma is the set of edges, and then we will use the notion of this dual graph, but the set of edges is the same. Okay, so then I give you an assignment of an angle. So for every edge, I give you a real number. And I want a rule that tell me if those assignments are good or not. So those assignments can give me a polyhedron or not. Okay? So given theta, a angle assignment, you can find a non-planar convex ideal hyperbolic polyhedra. Okay? Non-planar is that I don't want the polyhedra to be polygon. Okay? I want them to be real polyhedra. Okay? With one skeleton gamma and dihedral angle given by your map theta. So this is true if and only if the following three conditions are satisfied. Okay? So the first one is that I want the polyhedron to be convex. Okay? So the exterior dihedral angle need to be between 0 and pi. The second condition is that when you take a vertex of an ideal polyhedron, then you can consider a horosphere around the vertex. This horosphere cut out a polygon in your polyhedra, and this polygon is an Euclidean polygon, okay, because your horosphere has Euclidean geometry. And then we know that the sum of the exterior dihedral angle of an Euclidean polygon, it is 2 pi, okay? So here I'm stating a bit differently, because it will be related to condition 3. So here I'm stating that whenever you have a face in the dual graph, then the sum of the exterior dihedral angle, it is 2 pi. But we saw before that a face in the dual graph corresponds to a vertex in the graph. Okay? And then the last condition is the one that is a bit more mysterious. Okay? It took them almost 200 years to prove that. So this is not so intuitive. And so this condition is that whenever you take a cycle in the dual graph that doesn't bound the face, then the sum of the exterior dihedral angle is positive, is bigger than 2 pi. And so actually to prove that this third condition is necessary is not so hard. It's a Gauss-Bonnet type of argument. Okay? And also, if you know Andreev theorem, probably this theorem looks familiar, if you like circle packing or these things. And it's true because Andreev, in fact, proved this theorem for polyhedra, so for the case of when the angles is less than pi over 2. Okay? And yeah. You have a question?
Oh,
Yeah.
I thought you said Rivin's theorem was embedding in a sphere.
Yeah.
Oh, so okay.
So is somehow the point is that when your graph is inside the sphere, is inscribable in the sphere, then this corresponds to an ideal hyperbolic polyhedron because you put the hyperbolic geometry and okay, so somehow, and Andreev also proved for compact polyhedra, okay? The problem is that Igor argument uses a lot volume, okay? The volume of an ideal tetrahedra in hyperbolic space, it's a very good function with respect to the angles, okay? It's a concave function, and so he uses a minimizing volume argument, okay? In our case, the volume of our tetrahedra don't behave very well, so we needed to start from scratch. Actually, yeah, I will take the next, so at some point we wanted to prove this theorem using a twisted notion of volume, but then angles don't behave nicely, so we couldn't do. But that's still in the drawer of failed things, but maybe it has an interesting meaning. But okay, so now our case. Okay, so exactly the same. We have a graph. We have the set of edges. We look at the dual graph, and then we assign a number for each edge, and then when this assignment corresponds to an ideal polyhedron in these two new geometry, okay? So we will have exactly the three conditions as before. So the first one is the convexity, okay? And actually it is the convexity is the one that gives you the Hamiltonian cycle. Why? Because every face is space-like, okay? What that means, it means that the normal direction is time-like. And so the space-like, so the time-like direction can be positive or can be negative, okay? And if you look at all the set of faces that have a positive time-like direction, those form a disk. And the same with the other direction. So what you obtain is that you have two polygons glue along an Hamiltonian cycle. And that's because this is the convexity property, okay? So that's what gives you this Hamiltonian cycle, okay? Here I'm stating that the edges with negative angles, so the edges that behave like that, form an Hamiltonian cycle in your graph. And then the second condition is exactly the same as the one before. So we fix a norosphere, okay? So a norosphere in hyperbolic geometry was behaving like a Euclidean space. So let's say the tangent space at hyperbolic geometry is Euclidean. And here the tangent space has the geometry of Minkowski space, okay? And the Minkowski space, a polygon, the sum of the exterior dihedral angle is 0, okay? So here is exactly as before, but then the sum of the edges of the dihedral angle along a face in the dual graph, it is 0, okay? And then the last one is the same condition as before, but this time we restrict a bit because we have these two polygons, and then we look at all the cycle that doesn't bound a vertex, and then in that case the exterior dihedral angle is positive, okay? Feel free to stop me. And here I told you that Igor had the characterization in terms of metric, so the metric induced on the boundary, and we have the same, okay? So what Igor Rivin theorem is that somehow a polyhedra topologically is a sphere minus some point, okay? So if you give me a point in Teichmüller space of this sphere minus some point, which is the same as giving me a complete finite area hyperbolic metric, then there is a unique polyhedron which has this as the geometry of the boundary. Unique up to isometry, okay? Every uniqueness is what we could hope. And in our case, we have exactly the same, but we not only we need to prescribe the point in Teichmüller space, but you also need to tell me which Hamiltonian cycle you choose, okay? Let's say in the cube, you can make different choices. In particular, you have 3 choices of Hamiltonian cycle, okay? And then again, we have the uniqueness, okay? And now, okay, so now I want to show you how using our theorem and Igor theorem, we can prove what I call the main theorem, okay? It's a bit unfair to call it the main theorem because in fact, it will follow as a corollary of our other theorem, but it's a theorem that you can explain very easily to people, so that's... Okay, so the theorem is the one that I said at the beginning. So we have a graph. The graph is inscribable in the cylinder if and only if it is inscribable in the hyperboloid, if and only if it is inscribable in the sphere, plus it has an Hamiltonian cycle. And what I'm going to prove that H is equivalent to S, okay? And so let's start with S imply H, okay? S was the condition that we have a polyhedra inscribable in the sphere and we have an Hamiltonian cycle. And I need to show you that I can find the polyhedron inscribed in the hyperboloid. The way to do that is the following, okay? So by Igor characterization, whenever we have a polyhedron inscribable in the sphere, then we have an assignment of angles. So for every edge, I give you a number between 0 and pi, which satisfy condition 2 and 3, 1, 2, and 3. One is the 0 to pi, okay? And I have an Hamiltonian cycle, okay? So I think it's very clear what we should do. So think. So we have this second condition is telling us that the sum of the exterior dihedral angle at a vertex is 2 pi, okay? And we want to create a function such that the sum of the exterior dihedral angle is 0. But the Hamiltonian cycle, thankfully, give us a choice of 2 edges for each vertex, okay? So what we want to do, we start from 2 pi, we want to arrive to 0, we have 2 edges, we just remove pi from each edge in the Hamiltonian cycle, okay? And doing that, then we show that, so we define a new map that it does nothing on the edges that are not on the Hamiltonian cycle, and on the Hamiltonian cycle you take away pi. And then you show that these satisfy our condition, and so we won. Then you can tell me, yes, Sara, you show me the easier condition, right? So you already started with something between 0 and pi. Instead, for going in the other direction, you have angles that can be very big, okay? That seems harder. It seems harder, but in fact, what you can do is that you can scale it down. So you can see that the conditions are invariant under scaling. And in fact, actually, one of the proof, it will really be understanding when you scale down to what you limit, okay? Is a method of lines of minima that Kerckhoff used for hyperbolic geometry. But yeah, so in the other direction, you first scale it down so that the angles are between minus pi and pi, and then you add back the pi that you want. Okay, and now the harder theorem, okay? So this is a theorem that we proved, okay? And that I told you that we cannot use a volume argument because volume doesn't behave nicely. And then, so what we are going to do is that we are going to prove that some map are homeomorphism, and we will see that some we will prove constructively, some we will prove in the somehow the other way, that the second step somehow whenever we can't prove constructively. So what we do in hyperbolic geometry sometimes is proving that something is a local homeomorphism, proving that is proper, and then trying to show by hand that is degree 1. Okay, so Okay, so these are the map that I want to look. Okay, so the first map, psi of h pi, psi of hp. So hp polyhedra, so polyhedra in half pipe. I fix the number of vertices, okay, and I go into the space A. So A is the space of maps that satisfy our condition, okay. So if you want, so A is the space of map that satisfy our condition. In fact, somehow you define for all different graph, and then you glue, somehow is a space that has a bigger cell that you glue along somehow when the graph has no triangular faces and things like that. So I'm not going into the details, but okay, so this is the first map. The second map is the space that assign a metric, okay? So you have an anti-de Sitter polyhedra, and this time we need to consider also the flat polyhedra, okay? So anti-de Sitter polyhedra plus the polygon, okay? Why? So basically you have different direction depending on which Hamiltonian cycle you choose, and all these they collapse into same polyhedra. So map into Teichmüller space, and then the third map is the map as before, but starting with anti-de Sitter polyhedra. Okay, so one of the nice tools that we use is the notion of earthquake and bending. Okay, so this is a tool that in hyperbolic geometry we use it a lot, and it is the following. So whenever you have 2 points in Teichmüller space, then there is a unique lamination such that you can move from one point to the other by doing an earthquake. Okay, so what is an earthquake? Let's say here let's say that I describe for a closed surface. So you have your surface, you choose a simple closed curve, then you can cut along these curves and then move it, and then close it back. Okay, so if you had another curve that was small, if you had another curve that so this is the simple closed curve, and here I'm looking at the universal cover. Okay, so if you add some other curve that meet this, then when you do this earthquake, then it becomes this zigzag. Okay, and here is a picture where instead of doing earthquake, you do bending, because there is a duality. And I wanted to show you a little movie. So this is something that Jeff did. It's like, okay, so here we are doing this bending. Okay, so you have your hyperbolic plane. You look at the pre-image of your simple closed curve, and then you start bending. Okay, and what you get this that then for me will be quasi-Fuchsian space. Okay, and so again, okay, so this is the type of argument. Okay, and here we need to do
Surfaces?
sorry?
Just moving with surface.
Yeah, so the point is that here the picture was at the level of the universal cover. So
Of the computers?
oh, you are asking me which surface is that? I bet that is a S2, so genus 2 surface, but yeah, I don't know. But you can do for anyone, yeah, right? Yeah. And okay, so this is the point is that in our case we need to do a discrete earthquake. Okay, so we have a polyhedron. So okay, so the first things that one need to notice is that a polyhedron in anti-de Sitter space. So anti-de Sitter space, I told you that the isometry is PO22, but if you look at the conformal model, then the isometry space is PSL2R cross PSL2R. Okay, so every polyhedra, it gives you 2 polygons. So the product structure of the isometry group give you a 2 polygon, okay, 2 ideal hyperbolic polygon. Okay, what you can do is that you can double along the boundary, and so you can get 2 metric, so 2 points in Teichmüller space of the sphere minus n point. Okay, and then we now do this earthquake. So these 2 points in Teichmüller space somehow comes from your polyhedron with bending theta, if and only if they are related by this discrete earthquake. Okay, and now, okay, so this is one tool of the proof, and now let's try to give an idea of the proofs, and then I will try to look at some future direction from here. Okay, so the first map was the map from half pipe polyhedra into the space of angle assignment. Okay, so we have this half pipe polyhedra. I told you that is a limiting of somehow something that happened in hyperbolic space. In fact, a polygon corresponds to a polyhedra in half pipe corresponds to a polygon plus a deformation. Okay, that's why, because half pipe geometry you can think as the infinitesimal normal bundle of a codimension 1 hyperbolic space inside. Okay, so a polyhedra corresponds to a polygon plus a deformation. When you double it, so it corresponds to a point in Teichmüller space plus a deformation in Teichmüller space, in fact a special deformation, so in a certain direction, so in a Lagrangian subspace. And then somehow, like when I was saying that we use some method, we were thinking about what happened in hyperbolic case, so in quasi-Fuchsian space, then these lines of minima arguments, so we can solve actually in this case concretely by looking at a symplectic structure on our space, and then looking at the length and having a minimizing argument in that sense. Okay, and so we construct the inverse of our map. Okay, and so we prove that this is an homeomorphism. And having this concrete construction will be very important, because that will tell us that this space is connected and simply connected, which we will use later. Okay, so in the case of anti-de Sitter is more complicated, so it doesn't come from a deformation, and so we can't prove directly. Okay, so then we do the next things that we can do. Okay, so this second map was a map from anti-de Sitter polyhedra into Teichmüller space. Okay, and so first we prove that the map is proper. Okay, that we do it constructively. Okay, so we just look at what does it mean degenerating in the different spaces. Then we prove that this map is a local homeomorphism, and that's a nice argument using Pogolerov map. Okay, Pogolerov map are a tool that differential geometer likes it a lot, and it makes you translate infinitesimal property from one space to infinitesimal properties of the other space. And so then, since we know local rigidity of Euclidean polyhedra, then we can get local rigidity of our polyhedra. Okay, so properness and local homeomorphism give you that the map is a covering, and now we just need to show that is degree 1, and then Teichmüller space, we know it a lot, so we know that is a ball, and then we know that this space is connected, and so we can conclude. And now the last step, okay, the one that from anti-de Sitter to angle assignment. So again, the properness is a rect proof, and then to prove that is a local homeomorphism, we use the duality between metric data and angle data, okay? A bit like in hyperbolic geometry, you have lengths, and those are sort of dual to angles, okay? So in fact, you also have a notion of complex volume, okay? So, and here you have the same, but instead of complex number, you have pseudo-complex number, okay? So like a complex number, but the square is +1, not -1. Okay, so these give you this duality between metric data and local data, and then again, since we know that the topology of this space, then we can prove that this map is an homomorphism. Okay, and okay, so now I just want to, the last two slides I want to explain are a few other things that we have been doing, and the next one it will be what was the original question we were interested in. Okay, so this one is a project that we now finish it, and is an example of this transition geometry. Okay, so the Loni triangulation are a tool that have been used a lot and have been very interesting from many different viewpoints. Okay, so what are the Loni triangulation? So you have a set of points in the plane, you consider the convex hole, and then you want to triangulate the convex hole, and you, since you know that for any 3 points in the plane there is a unique circle, then you define the triangulation such that every circle does not contain any other point inside. Okay? But if you think a ball in Euclidean space is just a choice of the inner product, the Euclidean inner product, okay? So if you have a different metric, a different inner product, then you can define balls that will not be disk anymore, but that's might be okay. And so you define these balls that are hyperbola or parabola. So in case, let's say the Euclidean inner product is given by x squared plus y squared, okay? Or if you want x1, x2 squared, okay? But let's say here you can put a minus, and this gives the Minkowski one, or you can simply just have the generate one. And so anyway, so you can define the Loni triangulation for these new geometries, and then you can prove optimality properties. For example, the Loni triangulation is the one such that if you put all the angles in a list, it has the bigger, smallest angle. Okay, and here, you adapt the notion of angles, but you have a similar property. Okay, and it's very nice. So the way to prove it is actually you need to lift your problem to basically hyperbolic geometry or to anti-de Sitter geometry. Okay, and so now is let's say my favorite still open conjecture that my advisor when I was a graduate student was not allowing me to think. So you will be responsible of yourself, you can think about that, not now. So it's the bending conjecture. Okay, so we are now in the context of Kleinian group. So hyperbolic three-manifold, a very nice, a very important space is the space of quasi-Fuchsian space. Okay, so hyperbolic three-manifold that look like S cross I. Okay, and if you want, you can define as the one such that the limit set on CP1 is a quasi-circle. Okay, so those spaces. So you have S cross I, and so it's a important theorem by Burr's double uniformization. It tells you that this manifold is parametrized by the two copies of Teichmüller space at infinity. Okay, but hyperbolic three-manifold, they have an important subset which is called the convex core. Okay, is the smallest convex subset which keeps all the geometry such that the inclusion is an homotopy equivalence. And it's an important theorem by Tarson. It tells you that the boundary of the convex core is a pleated surfaces. Okay? So it's a surface like the one I showed you in the video. And so every pleated surface has an associated point in Teichmüller space and then associated lamination. Okay? So then you can ask, okay, so what about if I give you these 2 points of Teichmüller space? Do I still determine uniquely the tree manifold? And that's still open. So it's proved in some cases. It's proved in a neighbor of the Fuchsian locus. It's proved when the surface is 1 point torus, because if you think when you think about complex analysis in dimension 1, is very different than complex analysis in dimension bigger than 1. And it's proved in other cases. But anyway, so as I said before, so you have a question in hyperbolic geometry, you have anti-de Sitter, then if you think precisely how to translate, then you can translate the question. So there is a quasi-Fuchsian space in anti-de Sitter geometry, which is this globally hyperbolic, maximally compact space. And then again, there is a double uniformization theorem proved by Mess. And then again, there is a convex core, so you can ask again, this boundary of the convex core determine my surface. And but the problem is that in one case, here in the hyperbolic setting, at least you know if your lamination is along simple closed curve. So if your lamination is rational, then you know that the answer is yes, and it is because you double along the boundary, then you get a cone manifold, and then cone manifold are locally rigid, so they are parametrized by the angles. In the new context, actually, the naive way to generalize is not true anymore. So, so the idea that we had is that we would like to approximate this polyhedra, this pleated surface by polyhedral map. Okay, you will need infinitely many tetrahedra, but for example, Bonahon uses this approximation argument to prove something. Okay, so that's basically what I wanted to tell you today. Thank you.
Questions for Sara?
Yeah.
So in Igor's theorem, does he follow this same model of proving it's proper and a local homomorphism? He doesn't.
No.
So do you get a new proof of his
Yes.
theorem? Okay.
Yes.
Okay.
Sure. Yes.
That was sort of my memory, and I was. I never got into. I never really penetrated his paper because that was what I was expecting. I said, what's he doing?
Yes. Yes. So I think he has a second proof that is more simple than the original proof in his thesis. But so the idea he has is basically looking at the volume of an ideal tetrahedron and prove that it behaves nicely under the angles. And then basically prove that you can minimize, since this volume behave nicely, you have a minimization volumes argument. But we can't use those methods, so yeah.
You end up getting another proof. That's
yes. Yeah.
Can you just say a few more words about what these GH things are? I've heard of Mess's theorem, but I don't really know its statement.
Yeah, so globally, actually, is globally hyperbolic, maximally compact. Okay, so let me explain globally hyperbolic, maximum compact. So basically, you have your tree manifold, which is again S cross I, and so in this ADS we have time-like direction. Okay, so we want this sort of foliation with the surface that intersect every time-like direction exactly once. So this is globally hyperbolic. And then, because in some sense, small intersecting time-like direction means being in a space-like position. So we want these surfaces to be in space-like position. And then we want the surface to be compact, so in the case of a compact surface or with punctures. And then we want this to be maximal, okay, with respect, because somehow this will give us, in fact, a map from pi1 of a surface in PSL to R cross PSL to R, which will be discrete and faithful. But when you make it this rho acting on anti-de Sitter space, it will not act everywhere properly. Okay? It's a theorem of Cassel, for example, that the action of a representation like that is proper on the full anti-de Sitter space if and only if one factor is discrete and faithful, the other factor is not. Okay? So these will have this maximal domain of discontinuity for the action on anti-de Sitter space, and that's the space that you quotient by the action of your space. And the method, I found the method in general different from hyperbolic geometry, but in some sense you understand the dictionary. Okay, so you understand like here, for example, the mass theorem is really using the product structure. Okay, and instead, it's very different from Burr's uniformization, because Burr's was really complex analysis, and in some sense you can go back and forth, okay, because somehow these will be related to a sort of earthquake as well, so a fixed point of an earthquake, basically, yeah.
So Burr's parameters are end parameters, one parameter for the top, one parameter for the bottom. Mess's parameters are just this product parameter?
Yeah, so here you have a rho L, you have a rho L and rho R, let's say given by these two structures. And so the point is that basically small mass proof give you the existence of a rho plus and rho minus, so two other discrete and faithful representation, and then somehow now I can be wrong with the arrow, I never remember, but so basically you earthquake along, so you have a left earthquake along elimination L, a left earthquake along elimination mu, a right earthquake along the elimination mu, and a right earthquake along the elimination mu. So you have again, so you need to interpret what does it mean to have these splitted surfaces, but then you have this earthquake from one surface to the other, and then you prove that this earthquake have a fixed point, and then that's basically what it does. And the point is that the pleated surfaces are not really here, but the lamination is here. So the pleated surface, in some sense, you have this anti-de Sitter space, you have your limit curve, and then you have a product structure at infinity of the group, but you also have a product structure in the boundary. Okay, so the boundary is S1 cross S1 or RP1 cross RP1. Okay, and then basically the idea is that so you have this convex core, you have this boundary at infinity, which is not on the boundary like in Burr's, because you have this maximal, the action is not proper on the full space. But yeah, so it's the methods are very different. So, and for a while mass was not really very well understood, and he has an interesting story, and but yeah, unfortunately finished too early. Yeah, he wrote this paper, and then which is not so easy to read, but it contains a lot of very deep. But for me, coming from hyperbolic, so Jean-Marc and Jeff are small. They were more born as anti-de Sitter geometers. For me, the interest is that I like hyperbolic space, and so for me it's always interesting to see how to generalize and how I can use my method there, or how I need to modify my method there. And yeah, and we are thinking this summer to write a little book, because it's not so easy to learn about anti-de Sitter geometry. There isn't a good reference, so unless your advisor is an expert, then yeah, but yeah.
What is it? It's 2016, so yeah, 40 years ago it wasn't so easy to learn about hyperbolic geometry.
Yeah, exactly. No, it's true actually. Yes. Yeah, we have some graduate students in Brown. They were asking me reference, so yeah, we were. Yes. Yes, little by little.
All right, let's thank Sara again.
Thank you.